Hi, I'm Dave Robinson, and welcome to a bonus screencast where I'm going to be solving a puzzle from 538's Riddler column. I've done a few of these before, but this I think is an interesting puzzle. It's going to be a word and letter puzzle. I wanted to show how you could use R to answer a question that's a little bit not really statistics or probability or data related, but is more about working with text and letters. So I love that there are actually two puzzles in here. The Riddler Express is probably also an interesting one to solve with data, which is figuring out what each of these countries' flags are that have their pixels scrambled. I might look at that later, but this is a Riddler classic. We're going to be solving a spelling bee. So I just took a brief look at this before I decided to solve it in a screencast, and let's see how fast we can solve it. So it's the way it works. We have 7 letters in a six letters around one central one G. We want to identify as many words as possible where the word is at least 4 letters long, includes the center letter, can't include any letter beyond the 7 given letters. So letters can be repeated, and you get points for 1 point for 4 letter, 5 points for we get like 5 points for 5 letter words, 7 points. Words that use all the 7 letters are known as pangrams, and to be a valid choice of which 7-letter honeycomb results in the highest possible game score. Okay. To be a valid choice of 7 letters, no letter can be repeated. It must not contain the letter S. Must be at least 1 pangram. Okay, we're gonna try it. We're gonna try solving this set of rules by working in R on the tidyverse. So the fun thing is we're going to be using this word list to check our score. And what's handy about R is we can read these in directly. So I'm going to go in. So I'm going to do a tidyverse, and I'm going to say read lines. These are our words, but I'm actually going to put them in a table. So I'm going to say word equals this. So now I have a full set of words. Now, what are we going to do to work with this honeygram? In order to, or what is it called? Yes, honeycomb. So every word has to contain G. I'm going to be doing something simple to start off. I'm going to be filtering for, we're going to be using a lot of string R and per today. First, string R, the word must contain the letter G. All right. Now I'm going to get my other letters here. We're going to say, letters are what are they? A, P, X, M, E, L. A, P, X, M, E, and L. And then the main letter is G. Center letter G. I'm going to start by saying center letter. So now I have all the words containing G. How can I say it must only contain words from these letters? Well, here's what I'm going to do. I'm going to add a column called letter, actually, let's say 6 letters. I'm going to call this, give us a different name. And to say letters are string split word based on an empty string. So now I'm going to get a list column that says, okay, now I've split this up into 6, into 5, into 6. Why am I doing this? Because now I can work with vectorized approaches. I can say how many first I can say how many words, letters, invalid letters. What are going to be invalid letters? They're going to be ones that are in here but not in the 6th letter, in either our 6 letters or our 7 letters. I'm actually going to call this all letters. So I'm going to have the center letter, all letters. So set diff. Letters and all letters. Set diff is really good for saying set diff of like A, B, C, and B will be, oh, you remove the B, see the A and the C. Here we can say how many, set diff, my bad, I need to do map to, because I need to apply this to each of these items. So I'll say map to, and then say, here's what I'm going to do. I'm going to say invalid letters are map to letters and all letters. I'm applying the setDiff function to every pair of them. I just need map and the second letter. So what did I do there? I actually got a little confused. What I did say is say apply to every item in this list the setdiff function with the second argument being all letters, but I actually got that one backwards. It has to be, this is my bad. It has to be what is the what in, no, that is right. Yes, all letters. So this one has 3 invalid letters. So now I can say filter. There's actually a function lengths that will apply to every item in here. Invalid letters equals 0. So AGA. Oh, I should probably actually do another filter first and say string length. I'm doing this early because it's a little faster. Of word must be greater than or equal to 4. Be a little bit, just a tiny bit faster. Get some things out of the way early. All right, so now we have, these are some 43 winning words. Agama, let's check that. A-G-A-M-A, there we go. Counter including letter, yep, so that fits all of these. So I'm gonna add word length equals string. I'm actually gonna do that up here just to reduce the amount of time I'm calling something. Say word length equals string length of word. And now say word length must be greater than or equal to 4. So notice what I did there. I said, yep, all these. Okay. And now I can say, what is the longest word that passes this? So here I have my winning words. I'm actually going to throw in one more step. Say points equals if else. Word length, if it's 4, then it gets 1 point. Otherwise, it looks like it gets 4 points. 4-letter words are worth 1 point. 5-letter words, 5 points. 6-letter words, 6 points. Okay? And I'm going to arrange descending points. Here it is. Amalgam. But amalgam does reuse. Let's see. Words that use here's one I'm missing. Words that use all the 7 letters in the honeycomb are known as pangrams, earn 7 bonus points. All right, how did I miss megaplex? Let's see, because it looks like I did miss megaplex. Okay, let's see. What would set diff string split gaplex? What would that look like? 1. Yep, that would be here. Okay, so how did I miss megaplex? Megaplex is not in this word list. Okay. Is it possible that there's some capitalization issue here? Nope. Okay. All right. Which 7-letter honeycomb? To be a valid choice of 7 letters, no letter can be repeated. I also dropped I didn't use the S. Oh, okay. So the question here is not, sorry, so I discovered this, I was able to tell this one. The question now is, which 7-letter honeycomb, not which word gets 7 letters, results in the highest possible game score? That's a much harder one, and it's going to be a little interesting. That's a good question. Okay, so highest possible game score. Let me see. Okay, all right. So now I want to say, all right. All right, I'm thinking of a couple of ways to approach this. We want, let's see. Yes, okay. If I take my words, it was fun to actually walk through that. That was one example of some winning words for this. It looks like amalgam is the winning word in this case. But what is the 7-letter honeycomb that will have the highest game score? We can get the game score out of any particular letter right here. So, actually, that's actually something a little bit useful, is that I can take this, let's see. I can take this, take the center letter. So words, I'm gonna apply this right up at the top. That way, we're not going to, let's see, here we are. So that way I can filter and work trying to work as efficiently as I can. Oh, and let me apply the splitting right at the top as well. Okay, and now I can take my words. I don't need this step. I do need this step. And, but I can work from there. So then I'll say winning words. Oops. Oh, my bad. So what I'm going to do is take our winning words. Here we go. Okay. And now I can sum up the points. And that would get me the points for any given combination. So get max score function, here we go. Here are my winning words. Sum winning words points. And I'll take a center letter and other letters. And here's what I'm going to do. I'm going to change this to center letter, other letters. Why did I do that? Because I can vary it a bit more easily. All right. And so I'm starting to approach like a brute force approach here, where I'm saying like, here we go, get max score. We say get max score G, and then I apply all the other letters. And I'll say G and our other letters, and it'll tell me the max game score that we can get. All right, and just to take a look at that, that was here. These definitely all look like valid ones. So I can say descending points, amalgam, gape, there you go. All right, so these all have the center letter. Okay. Here's what now I can't possibly try every combination. Now they say I can't use an S. So I'm going to use some heuristics here until we can come up with a better approach. They say I can't use an S. And that gives us 25 letters. But there's no way we're going to try all 25 to the power of, well actually no, I'll take it back, it would be 25 possible choices for the center. And then we have how many n choose 24 remaining ones, choose 6 for the outside. There are 3.3 million possibilities. That's a lot. I doubt we really need to go that far because the center letter is probably going to be something really pretty, the center letter is probably going to be a really common letter. Maybe a vowel, maybe a, let's see. Good. Yeah. Ooh, I missed the 7 bonus points. That's actually pretty important. So I can say, let's see, I need to say something here where I'll do mutate unique letters map int. So what I can do is apply to the letters. Oh, I can actually, this is actually something useful. I can do this up here because it's something that's only applied to the word. Apply to the letters, apply n distinct. So now I can say, here's how many unique letters are used. So this word uses 7 unique letters. Why do I do it that way? Because if because then I can say add to the points 15 times, are the number of unique letters, are they, is it equal to 7? Because if there are 7 unique letters used, then it's a pangram. So megaplex would be worth 15 points. So 15 times this, okay. And that will not increase, so that, there we go. If else, if it's 4, then it's 1 other's word length. 15 points if we use all the letters. That won't change for my current approach because we actually didn't have any pangrams. I think that'll still be 153. If there were megaplex in there, then I believe it would. Okay, so what am I going to look for? How am I going to approach this as a heuristic? Okay, well, here's what I'm going to start with. What are the likely best letters I want to use for the center? Remember, every word has to contain the center. Well, let's take a look at our. I can compute the points up here. So notice I took the word dictionary, and now I'm saying, aha, AAS Vogel. If that's a valid word, if that matches, then it's got 7 unique letters worth 23 points. One thing we know is that if there are more than 7 unique letters in the word, it's not going to. Here it is. Yeah, this is impossible because it has 15 unique letters. So filter for unique letters. We're looking for the dictionary that applies to this game, and that will always have 7 or fewer unique letters. And now I'm trying to reverse engineer the honeycomb that will allow as many of these high point ones as possible. I'm also going to, just for us, I'm going to arrange in descending points. So the most points you can get. Wow. Interestingness is worth 32 points. So if we had a honeycomb that covered interestingness, we would have, setdiff is going to be a little bit faster if I do this. If I say letters equals, and now I'm going to apply one more function to letters. Map letters unique, and now I can use map into, or just lengths of letters. Here we go. So now I can say the word length. Yep, now I've got this vector of 7. That actually doesn't make a big difference if it makes it a tiny bit faster in the later steps when we do setdiff. A tiny bit, it probably doesn't really matter. But it makes some things a little bit easier. Okay, so something I might be interested in is what is the average points for each letter? This is not going to give me necessarily that each letter is worth. That is how this suggests, for example, I can already see that. Oops, do I do a filter for G? No. Wait. Oop, I did a filter for G at this step. I can't have that because that happens down here. Here we go. Disinterestedness is the best word in this dictionary. It has it uses only 7 letters, but it uses all unique 7. If we match up our combination to this, then we'll have a really good set of points. Okay, that's something that I wanted to show. All right. Yeah, but there's only one. Remember that for each of these, there's only one honeycomb that would match for each of these. Still, I think it's going to be a little bit informative. I have my max score here, but what if I take a look at my words? And what if I say, I'm going to save this, honeycomb puzzle, okay. What if I say unnest letters? I found unnest strangely slow recently. I'm not sure if it's just me, maybe it was never any faster, but then I group by letter and I summarize total points. Wow, that is pretty slow. I could start by saying, like, what is the total points that this letter covers? So I can say, like, we'd give the letter E 34 point. Let me see. I'm going to actually. That's a little strangely slow. But I'm going to say unnested words is unnest letters. Oof. That is slow. What if I tried just select just these two. Oops. Letter. And now, okay. The top 100 worked. 500. 1,000. 10,000. Really does get slow, doesn't it? It's a little strange. Really look into that. It's a shame because I don't have, actually do have another way of approaching this that I believe, which is to unnest tokens on it. I wonder if that's actually faster in this case. So what if I, it might be, so this is the kind of just a hack that I'm trying out. I'm taking tidy text and I'm going to say unnest tokens, letter, word, token equals characters. That was way faster. Okay, so I think something's up with the unnest function. The unnest tokens doesn't use unnest on the inside, so that's why it gets to be faster. It takes a couple shortcuts, but that's really odd. And I'm going to add remove drop equals false to keep the word, because I need to say distinct word letter. What we need to do is say what I need to do distinct, because this will count the same letter multiple times. Here, disinterestedness has, so here's what we're trying to do. Disinterestedness has 7 letters. Here goes D-I-S-N-T-E-R. Now, every one of those, it's useful that there is distinctiveness. It's useful that it's in disinterestedness. That is like a useful fact that means that each of those letters is probably pretty good. So what I'm going to do then is group by letter, summarize, and words equals n, and points equals sum points. I really need to report something about the unnest. Maybe I got the wrong version of tidyr or something. And remember, this is not, it's not saying that if you include this honeycomb, this in your honeycomb, you're going to get all these points. It's just saying like this is the maximum points you can have if this were your center letter. And these are the points that words that might become available to you if you do use them. It's a kind of a greedy one-letter approach. It's ignoring all the combinations between letters. And I'm going to arrange descending n points. So here I'm saying words, letters, summarized. All right, good on unnest tokens. Makes this pretty fast. So this doesn't surprise me. I actually expected, so S is really high, but remember, we're actually forbidden to use S. But E is the best letter. It covers 900,000 points. So just in terms of, if we're going to pick a center letter, it probably wants to be E, maybe I. They cover a large number, they enable a large number of points. If I view letters summarized, I bet like X and J, probably even J might be the worst. Yeah, J is the worst. You're definitely not going to use any of these letters. Why would you do that? They limit your total like universe of point questions you can use. Okay. You know what's interesting about this? This is actually kind of interesting. Okay, I think I might have an approach now that I'm thinking about it for solving this puzzle, which is that that notice, here we are, we've got our, I'm going to split up this into 2 steps. So this is letters unnested, letters summarized. Okay, and now I've got letters unnested, letters summarized. I'm going to look at my letters and nest it, and it's occurring to me that this could be a, how many words are there? About 100,000? This could be a 100,000 by 25 matrix. It could be a sparse matrix, but it probably doesn't have to be. And once it's a matrix, that might make some of that, that calculation a little bit faster. So some of these calculations around what is the best possible honeycomb. It might. I'm thinking for a second about how I would do that. Yeah, I would have to say, let me see, I'd have to multiply it by the, oh, yeah, this could be quite interesting. Okay. I just know that if I make this a matrix, I'm going to end up, I think, a little bit happier. What I'm going to actually do is use a live package that's not used very often, which is reshape2. Reshape's acast function will let me turn this into a matrix. I find I still have usefulness for matrices, especially when I'm trying to do fairly fast operations. I want every row to be a word and every column to be a letter, and I want to fill it in with length. So it's going to have like ones and zeros all the way through. So word matrix. Now it's using letters. Oops. Value.var, and I need fun aggregate. Well, fun aggregate equals length. Actually, so this is kind of an old school way of doing this. It's like aggregating within every combination and then getting the length, which just means it's going to be ones and zeros. So here's what the shape ends up looking like. AAHED ends up hitting A, D, E, and H. This doesn't cover my uniques, but I'm going to cover that. I'm going to worry about that in a second. Okay, and then I'm thinking now about how could I say, how many letters does this cover? The problem is I really need the negatives. I really need to say like there's no, I was thinking about doing this, turning this into a matrix multiplication. But what I really want is the negative of it, which I can also get. I can do, okay. Okay, so this could be kind of cool. I'm just thinking for a bit how to do these matrices. How would I get the word score from here? I would say, first of all, word matrix. I can only use rows. So I'm looking at right now the head of word matrix. But what if I said that word matrix G had to be equal to 1? This is, comma. I select only the rows that there must be a G. Okay, I can start with that. And then I can say, how do I apply these six other letters? A, P, X, M, E, L. Well, I'll turn them into a vector. How to turn them into vectors? Say other letters equals names of word matrix. That actually be call names. Got it backwards. Call names of word matrix in other letters as numeric. Now I get ones and zeros. I'll make that as integer. May or may not be fast. So what I get now is we say A, G, A, P, X, M, E, L. There's the X, for example. So now I can say, okay, those are the letters that are permitted. So this would be my permitted letters. But how could I say not permitted letters? Well, I could do a, let's see. Yeah. I could do a matrix multiplication. I could say, here's my word matrix. Okay. minus this, this is all the letters that are forbidden. And then if I do these are all the letters that are, if I take the letters that are present and multiply them by the letters that are forbidden, I can actually get, here we go, word matrix multiplied by 1 minus the permitted letters will get me the number of forbidden letters. Here we go. So AAHED, what happened right there? What I said is multiply this vector by this column of the forbidden letters, and it actually got 2 overlaps. It has a D, it has an E. No good. So then we have our, so we can say, okay, if these are the permitted letters, here's the number of, here we go. Yes, we said if these are the permitted letters, then here's here are the ones that are forbidden. So but then I can say what words are num forbidden. So 1 column matrix with 1 item for each row. Is this right? With the words that were filtered, you get 98,000 words that are possible, that are in our vocabulary, that are possible. I bet the center letter is going to be even. We're going to get back to that in a minute. Right now I'm still looking at the one with G. So then, but this is going to tell me, yeah, there's 2, 4, 2, 1, 2, 1. This is going to be my vector of here's how many words are permitted in each. Are forbidden in each. And then I can say if I looked at word matrix, but only at the rows when num forbidden equals 0. Now I get the ones that pass. Oh, but I also would have to say, what I want to say, and G is included. Num forbidden. Oh, because G is not in my, silly me. G has to be in my center letter, other letters. Gotta recreate both of those. Here we go. And now we get a gamma using 3 letters. That gets us 5 points and so on. Now we get our number of points for each. Now we get our words for each. And then we would just have to add in, not trivial, but we would add in how many points are applied. Okay, so we're doing this as a matrix, we're starting to move towards this matrix multiplication. That's good news because matrix multiplications can be very fast in R. What I do is there's a couple of matrix multiplications. I'm going to start by saying, let's see. I need to then say the number of points that are included. Let me see, yeah. So here's my word matrix. So first I'll say, here's my word matrix. Points, word, I'm adding one more value. We're saying points, word matrix is going to be, I'm using what I'm going to say is it's going to be our words points when we created that words data set. Points per word, I'm going to actually call it this. And say names of points per word are words word. Why did I do that? Named vector. Disinterestedness, coxio, wow, that's a long one. And now we have 6 options. Now you can see like here for each of these, the number of points for each. And now I can say, then we say points per word is take this and index it by the names of the word matrix. Now it lines up 1 to 1. Row names. I gotta do these 3 over again. There probably was a simpler way I could do that, but what I want to do is say, here's our points, here we go. This gets 5 points, 6 points, 1 point, and so on. So then I can say, what was the max points per word? It was that one that had 34 because you even got a bonus. we're still using that earlier points logic. But yeah, this is the key matrix multiplication. We said, here's our, one moment. No, this is not a matrix multiplication. This was getting our vector of letters. And then we were saying multiply, this is our core number forbidden for each word. And now we say points per word, index that by num forbidden equals 0. And we can see here's the ones that won. There's amalgam in there for 7 points. And we sum this up, we should get 153. Whoa, look at me going, not getting anything right. Oh, notice I was missing that G condition. I need to say word permitted is this, and word matrix, here it is, center letter equals 1. This is a numeric vector. This is a logical vector, saying the first 6 words cannot be used. Here is my sum 153. Why was I doing all that? Because it means that I can do, here I am, I'm going to say get score center letter other letters. This is going to be way faster than my earlier filter, the set diff based approach. I'm pretty confident it'll be a good deal faster, but let's find out quickly. And then it's actually giving me even more ideas for how I can work with this. So I'm going to say get score of C, and I still have my other letters set up. G, 153. So now notice that was a good deal faster. I'm still going to be speeding it up a little bit more. I just wanted to show how we could speed this up by saying, do we even need this step? Probably not, because it'll automatically, it'll read it as a matrix. So notice this says like, okay, here are the permitted letters. Here's the number of forbidden letters across all of those. And then here's whether the word is permitted because it has the center letter and there's nothing forbidden. And then you sum up the points of those words. This only worked because we originally set up our word matrix, where did I set that up? Here it is. We originally set up our word matrix and we set up our points per word. Lines up with rows of word matrix. This worked because I'm going to separate this chunk out and say, here's our word matrix, here's our points per word, here's how we get score G, and with all of our other letters. And now I've got a hypothesis here, which is E is already one of these, but R is not one of these. And we actually saw earlier that in our letters summarized, R was one of our best. We can't use S, but R and I are both pretty good. I'm going to see if I change this to R, does it go up from 153? Wow, goes way up. What if I used I, even higher? No, a little bit lower. I think that's because it already had 2 vowels in there, A and E. What this can do is say if we kept our other letters fixed, we could get a higher score by saying, well, let's use I as the center letter. Okay. But what if I said, here's the thing, I'm actually going to be dropping S completely because we know we can never use S. We can't use S in any of the letters. So I'm going to say filter word length is 4, not string detect word S. This is actually going to get rid right away. It's going to get rid of all of our disinterestedness and things like that. It gets rid of those right off the bat. And it's going to improve our, it's going to actually change a couple of our results here, including even letters unnested, letters summarized. Could even change the order. doesn't too much, but yeah, it removes s from the equation. Okay, we're looking only at words that don't contain s. We see that E, I, A, R, N, T, those are all some really, individually it looks like those cover a lot of ground, but we really want a combination of them that are going to be unusually strong. I'm still going to try just to, let's see, this should still be 153, good. What if I said, let's use only the, let's try as greedy an approach as we can. Use E as the center letter and I, A, R, N, T is the 1, 2, 3, 4, 5, I need a sixth. P, L. Whew, look at that. This combination, this honeycomb allows a score of 3127, which, wow. That's quite a score. Something I'm going to do at this point is I like checking on these results a little bit. So I'm going to change this earlier function. I don't need get max score. I'm going to change this to get words. And I'm going to, here we are, arrange this. We don't need it because I can get the points with that lower function that's actually a little bit faster. Descending points. And I'm just going to return those. So I'm going to get, here's my get score. What if I get words with the same center? It should, they'll add up, should add up to 3,000. Notice, wow, there's 482 words. Anti-literate is a 27.1 that becomes available when you offer this combination of letters. Interlinear, interrelate, and so on. So how long does it take to run this with my matrix approach? I'm taking a quick look. Not a ton we could do to speed this up. There's little improvements I could make, but they're not. But it's going to be the matrix multiplication is the hard part. And I wonder how long does this take to run? So if I did micro benchmark, I'm just going to do here of this get score. That's probably going to run it too many times. It looks like it takes about 23 milliseconds to run. I'm going to try it 100 times. Or no, median 50 milliseconds. You can do 20 a second. Sounds pretty fast, but it is really really impractical when you're looking at 20. Well, if we're moving S, and let's say we know that it's going to be E, let's start by fixing E. It's still really impractical. It's still it's still choosing out of 25 24 letters, even if we're dropping E6. But in practice, we're only going to use, say, we're not actually going to try. I think this. Okay. I have a couple approaches I could try. I could experiment a bit more, try and find something better than our E, I, A, R, and our like completely greedy approach, which gets 3127. I could try randomly varying it a little bit, as in try say only look at within our letters summarized. Look at our top 10 and pick let's say 9 besides E and pick 7 among those. How many ways did we choose 7? There's 36 of those, and that's a little bit more doable. How would I go about doing that? Yeah, how would I go about doing that? I would do comben. This is kind of this is a neat approach. What I can do is do take my letters summarized, letter 1 to 9, and say I want combinations of 6. Did I do 7? Oops, I need 6. It's going to be a good deal higher. Still going to run. This is now every combination. There are 84 combinations of the 6 letters that are in our top. Oh, not 1 to 9. I wanted 2 to 10. I wanted the next 10 that are in our top combination. So here's our letter, our good. Let's say we use these top 10 as our good letters. We probably want to go a little bit farther than that, but I just want to note these are our good letters. Okay, And then I say for each of those combination of good letters, I want to take I want to apply this function to get the center letter with the center letter E and that other combination of letters. There's actually an apply function I can do that will apply this to the columns. Does that work if the result is a list? Man, I cannot remember. It's been a while since I used this. I'm actually going to do it with map. I'm going to say map seqlen n letter combinations, good letter combinations, and call of this, along this, I'm going to apply the function get score of E and the letter combinations that are that column. This is a bit messy, but what I'm doing is I'm like applying the, and every one of them is going to be an int. So I'm just going to apply this. Oops. Map DBL. Somewhere in there, there's a, somewhere there, there's numeric instead of integer. And now we get all of our max scores. Oh, we actually find out there are indeed ones that are better than IARNTL, that first combination. That had 3127, we saw that earlier. But here there's 3832. Actually notice something as we get, because of the way the comben works, we end up getting smaller and farther and farther from our top few. Like this last one, NTLODC, because of the way it was ordered that I gave it, that was rows 5 through 10. And that would be, so that's like a little bit worse, avoiding some of our highest like coverage letters. And notice, man, those are getting a little bit, those numbers are a little bit lower. What is the highest number was, let me see, I'm gonna, scores. I'm gonna apply, I'm gonna split these up a little bit, okay. And here are my scores. What's the max score? 3832. Okay, and yeah, that's the third one. And I can take a look at our good letter combinations. To apply which max scores. That's a fun one because which max scores is going to be the third one. There it is. It's a fun base R function. And say this would have been the combination. If I did get score of E and this combination, IARNTD, it gets 3832. And if I did get words instead, notice I'm still keeping the E the same. I want to get back to that in a second. If you get words instead, yep, now we're doing, now you can see the reason it's winning is it has 585 words. Entertained, itinerated, sure, yeah. Notice something about that, it actually, yeah, it has an I and an A, and then the rest are consonants. All right, that's detrained, entrained, entreated. All right, that's pretty cool. That's what that would be our score of 3,832. Now this was our maximum from a solid number of we tried our 84 different combinations that we had a good reason to believe were unusually good, but that definitely is not proof. It's not. For one thing, we were only trying E as the letter combination. Here's something we could try instead. Imagine I said pick 7. Here we go. And then get score. Wow, this is getting a little bit messy. I might clean it up later. 1 and then everything but 1. And that was what we do. We'd actually be picking, the first one would be our center letter and the rest would happen after. And actually maybe I want to change this. Yeah, I actually want to change this. So it just gets letter, honeycomb letters. here we are. And get this center letter is always the first one. And then we say, honeycomb letters is the first one. Now we have this, and we say call names in this, num forbidden. All right. And now we would say get score. I just was tired of treating it separately. That was kind of a hassle. 3127, good. Now this I'll need to fix. I'll get back to that one later. But all right. And now I can just give it our apply get score. So now I'm getting combinations of 7 letters. And I'm doing it with all the first 10. 120 possible combinations. All right. Oop. Oh, get score of, I still need to do good letter combinations, that column. Do it for 120. So now we're trying 120 different combinations of these top 10 letters. And we actually do get the same one. Because when I look at scores, it actually is, this is the one that goes where E is the first one. Looking pretty good. The one, when E is the top letter, it tends to do a little bit better. I'm going to add in an 11th letter. I'm just like experimenting a little bit with this brute force approach. Later we can then try optimizing it a little bit. Here we go. And call, how many are there now? 330. Okay, I'm still going to run it. I'm curious, like if I tried running, get rid of this. If I tried running, let's see, Sequelin and call. Really feel like there's like apply columns. So apply would work here, but I think apply wants a vector back. And oh, we have a vector. What am I doing? There is an apply function, which I think is which at least makes this a lot easier. What I'll say is apply to good letter combinations. Along the second margin, that is columns, this is a base R apply function. Apply the function get score. Trying to make this a little bit easier. I do a lot of refactoring like this when I'm working on a problem. So I'm taking the 330 combinations to every one of those columns, I'm applying and getting the scores out. And then I can say, what is the max score that is possible? And what is the, ooh, look at that. By introducing an 11th letter G, we actually did even better. So E is still the first one, the center column, but yes. It suddenly just hit me, which is that E is actually going to be, this is independent of order. So E is almost, E if it is present will always end up being the center letter. This is not actually that rigorous. I haven't tried this with I as the center letter, for example, or A as the center letter. So that is one issue. Maybe we'll fix it in it. We could try fixing that, but I just want it, but we might need to make it a little faster before we do that. But this says, okay, we don't necessarily want to stay to the top 10 because by introducing the 11th, we did get an improvement. If I said here the top 12, how many are there now? 792. I'm still going to run that just to like get a feel for it, but I'm definitely seeing that like brute force, we might still use brute force to solve this, but this is it's definitely getting a little heavier. So we have a couple choices. I could keep trying to optimize in here. I'm not. I don't know. I could. Oh, there's my integer. Is there, and then I could say this. I wonder, is this an integer matrix? I'm trying to speed it up just a little bit. But it's really not. It's not going to help all that much. Most of the time is being spent in this multiplication. It is really pretty fast. 50 milliseconds for an operation like this is fairly fast. But what I want to notice is that like this could actually be here we still, it looks like when you add 12 letters, whatever the 12th letter is, doesn't work. Yeah, it's an integer. I'm just speeding and doing little micro optimizations. Num forbidden should be integer matrix, integer matrix. Yeah, all this is an integer matrix. Okay. All right, one thing I want to notice though is I'm still applying this to one vector at a time. And that's probably not quite right. Probably what I want is to turn this into a matrix multiplication. Yeah, I'm definitely seeing it now. I want to do, here we go. I want to do a matrix multiplication on not just on one set of permitted letters at a time, but on several combinations. All right, so how would I go about doing that? I'm going to grab this column. All right, I definitely want to start with the center letter always being E. Okay. Okay. 1 second. One sec. Yeah, I'm still recording. Yeah. So let me see if I do. Let me see. Yes, what I want to do is create a matrix of these good letter combinations that that has turn this into a binary matrix. So good letter combinations. What if I don't include? I'm gonna make this a little bit simpler. Don't include E. Don't include the top one, and then say here we go. 1 to 6. 1 to 6. All right. Oh no, I don't need 1 to 6. I just need good letter combinations, and yeah, these are all of our possible 6 ones. What I would then do is apply to each of these columns the operation function call names in this. Let me see. What I'm going to do is apply the function call names word matrix in here. All right, and then what that'll do is turn this into, this is a 25 matrix. Let me see, length of this. Okay, and I always want E to be included. So what I do is say E, take my good letter combinations. I'm actually gonna, can I bring in an E? I don't know, I'm gonna say, I'm just gonna do it here. And then say scores are, oh, no, this is not scores anymore. This is going to be binary matrix. And what this is going to do is then say, I'm actually going to view this for a sec because I think it's actually pretty cool. What this says is here's, every column is now one of our combinations. It's going to be trues, falses, trues, falses. Why are there 26? I thought there were 25 with the, I didn't apply the S step yet. So let's see, so good letter combinations. I didn't reapply letters summarized. Or I did, but I didn't reapply this one. Oh no, I didn't reapply the word matrix. Here it is. Word matrix. 25 columns, there they are. And now I can create our binary matrix. Multiply it by 1, which will turn it into into trues and falses. Look at that. So this says we have E, there is an E included, there's an A included. This is now, yeah, and we can see that A is included for most of them. It's a little odd. Why is A? Oh, because I'm only showing a limited number of columns. Okay, and this is for all the 84 combinations that you always using E as the top letter. And I need to figure out the E. I'm going to need to figure out separately. Okay, that's a binary. That is a binary matrix. And notice this fits really well with the word matrix. Instead of 1L, I'm going to say 1L forbidden matrix. Here we go. So here's the forbidden matrix, and now we can say, here's the, let me see. And now it'll be ones everywhere except those that are 0. And then I can take, these are the, for each every column here is a possible honeycomb. One of the 84 possibilities we're trying. Every column is one of the 84 honeycombs.
Are you
Yeah, no, I'm recording, yeah.
Oh, sorry.
Yeah. Every column is one of the 84 honeycombs. And then each row is a, each row would be a letter and a 1 if it's forbidden. And that is really cool. Why is that cool? Because I take this and I multiply it with our forbidden matrix. And is word forbidden matrix. I'm actually going to call it awesome. I'm going to say word allowed matrix is when this is equal to 0. Because this is now saying for every combination of a word and whether it's forbidden, 1 to 10, 1 to 10. I'm going to look at the top 10 rows. Yeah, this is saying in these first 10 combinations, the word AAHED, ahead, is forbidden. And then here it is, it's always forbidden, but here it'll pass in this combination, it'll fail in these, it'll pass in these 3 combinations, fail in these. All right, really, that's actually, this is getting me a lot closer. I actually can try saying here, let's do it actually up to like top 13. How big is this? Now it's 924. We apply this logic for the forbidden, for every one of them, is this forbidden? And now we have 924, and now it'll matrix by 25 by 924. 25 letters by 924, is it forbidden in this combination? And, word allowed matrix, so it's actually this. Problem is I keep running into that center letter issue. Word allowed, is a word allowed in this combination? Yeah, what I have to do is actually then apply to every one of these. I have to apply, so take word allowed matrix, and I have to actually multiply it by the single vector that does the word matrix, does the center letter, which is that right now? E, did I leave it as E? No, I left it as E. Well, I'm going to say word matrix E. So this is going to be, here's my, what does it contain an E? So aimfully would be missing, but ailed would be successful. And by doing this multiplication, it actually applies to every column. Well, that's actually cool. Yeah, okay. I can make it a 3-dimensional matrix by trying out different centered letters, but that's probably overkill here. And then what I would do is take our word allowed matrix, multiply it by the word matrix E, like it is the letter E in here, and then here we go. I would take this. This is still, I always check the dimensionality of matrices as I go. Word matrix. Why are there only 44? I guess they removed all the words that had S's. That made it smaller. With only 44,000 words that didn't have an S? Awesome. Okay. Just wanted to check in on that. Okay. And then now we have 44,000 words. 84 combinations that I had not rerun. This and this and this. It's taking a little bit longer now, but here we go. 44,000 words. In every one of these, is it allowed? And now, this is the really sweet part. We multiply this. What else do we have that is this length? Well, we had these points per word. we have 44,585. We want to provide points for every single one of those words. So what I'm going to do is say multiply this matrix by points per word, which then will take our matrix, which right now is words by combination, and turn it into just 984. I need to I need to not make that a dimension. I need to transpose it. Yes, I need to transpose this to say, and now I have my 984 scores. Every one of these represents one of those good letter combinations. When I say good letters, like really any letter combinations. So here, boom, this one was E and those other 6, and we see that was the score. And look at that, we computed 924 scores at the same time. And then I can say, what was the max of, call this scores. I really turn it into a couple of matrix multiplications. This was, notice on matrix multiplication, this just added a center letter. All right, and then we say max scores 4169, and then here we are. Look at that. It was in this combination. We still see that AIAR NTG out of these top. Out of all the ones where E is the center letter, I'm actually going to, while we're talking, I'm going to increase this a little bit. And this is now, I need 6 combination of those. Of the 14 letters besides E that we think are probably best. And this is taking a little bit of time. It's also going to use a lot of memory, because word aloud matrix is going to be pretty big. You know, if I filter for the center first, we're going to get a little bit better. Okay, yeah, it's going to get a little bit faster. I'll notice even when I added those, it still wasn't any better. Here's what I'm going to do. I'm going to say filtered word matrix. We filter for the center letter. Word matrix. It's not quite as elegant because not just a couple of multiplications, but it's not like this step was all that incredibly beautiful itself. What I'm going to do is say, take our word matrix where our E, which is our center letter, matrix, the E column must be 1 and only take those words. And this makes it a smaller matrix. So I take filtered word matrix, word aloud matrix. So filtered word matrix is for every word, does it have this letter? Word aloud matrix. 28203. So now it looks like there are 3003 combinations up here. We had this out of combinations of 6 letters. There were 3003 combinations, and now we have for every one of those is the word permitted, and we say, well, multiply that by the points for each of those words, and we end up with our scores. I have a feeling it's still going to be 416. Aha. Yeah, that matrix didn't end up lining up with it anymore, I have to say. It's not really quite as elegant as it was before, but a little faster. Scores. Still 4169. I have a feeling that none of those lower letters are really going to get us anywhere. Because remember, if we look at our letters summarized, if I'm looking up to the 15th most common letter, that's like B, and that just covers a much smaller set of points than those higher ones do. It could still have interactions with the higher numbers, but like with higher letters, but it's just very unlikely. All right, look at that. Now so we've seen like when E is the central letter. When E is the central letter, then let's see. Yeah, when E is the central letter, then the best combination is E and these 6 letters. I think again, didn't actually do brute force on every combination, but I did it on all the best. I combined in that heuristic of it probably was an individually common letter. And we haven't seen any letters beyond G we haven't seen U, M, P, or B be useful. So that was worth knowing. Okay. But that was just using E. So I'm going to test this one more time. Center letter. Let's see. So that was using center letter of E. And I'm going to try it again with I. And we can, here we go, change this. And maybe we could turn this into a function. Yeah, I'm going to turn this into a function. Find best combination. And I'm going to apply a couple things. What I'm going to say is center letter possible letters. So I'm going to create this function for taking some center letter, in this case, we were using E so far, and then saying, here's my other possible letters. It'll be a subset of the rest of the permitted letters. And then we'll look at, here it is. We'll apply it through those, and we'll say list center letter equals, I'm continuing that, center letter score equals max of the scores, and I'll say other letters equals this, and there's our max score. So now that's a way I can find best combination. So if I applied find best combination to E, and then, well, I'll use letters summarized 2 to 10. This finds IARNTD has a score of 3832. If I apply it to 11, now we get better. But if I say the top 12, it doesn't improve it. I'm going to bring it all the way to 16, even a little farther. This again is going to take a while. It's applying a couple of big matrix operations, but it maybe makes us feel a little bit better that about that heuristic. I'm feeling this. I think there's a good chance this is the best global, but I think I want to try a few other center letters after that. Okay. Yeah. Okay. What I do now is try applying I, and what I'm going to do is set diff of these and I. I think it's the second one, but it's just too difficult to deal with that. So I'm going to say is the other possible letters besides I. I'm going to make this a little smaller so we get it a little bit faster. Get a solution a little bit faster out. And then it'll say here are the pool of the letters that it's trying out besides those. I'm just checking all my math here. Yeah, so it looks like when the center letter is I, it's going to find that EARNTG. It's actually take a look at that. Oh yeah. It's the exact same combo, except I becomes the center letter, and the score is a little lower. So that is a reason to think. Let me see. I'm going to apply that. So pool. I'm going to call this pool is the head of the 16 best letters, and then I'm going to say is set diff that with the pool and E, and here I'm going to say set diff pool and I just wanted to to make this a little clearer what I'm doing. And now what I'm going to say is we used we used I, letters summarized. A is the third one. Okay. I could apply the map function here. I could make it more elegant, but maybe I will later. But each of these steps is taking long enough with this tremendous matrix multiplication that I'm just kind of taking it a little easier. Look at that. A actually has the exact same combination of 6, EIARNTG, but with the different center letter. So just keeps finding and then actually even an even lower score than it was with I. I'm going to try R, but that really is making me, it's strongly making me think that there's no better combination of 6 letters, and then there's no better center letter among those than E. I'm starting to think about this a moment. Is that the way that this, oh, that is better. Let me take a look. EIANTG. 4298 was that? Oh, wow! Look at that. That is better than our center letter of E. If our center letter is R, then EIARNTG. IERANTG. That's really cool. Actually, I really didn't necessarily expect that. And I'm gonna throw in a T here. Oh, sorry, an N. It's the next best one. We're doing them sort of one at a time. Oh, that's actually not the best next best from the. Oh no, it is the next best. I did EIARN. And I wonder, is it going to also be EIARNTG? EIARNTG, yes. But it's actually a better center letter than I or A was. And is it a better center letter than E? 4169? Yeah, it is. So this actually, so one thing this is making me think is that maybe the way to approach this is first say what is a combination of 7 that is best, and then say among those what is the best center letter. I'm not sure it works that way. I haven't thought it through enough. But it does seem pretty clear that this is a combo of 6. That is something special. But then yeah, within those, wow, it definitely is. These are some better ones. Okay, I wonder. Oh yeah, I could have done a 3-dimensional matrix. Multiply this by. I'm actually quite bad at thinking or working with 3-dimensional matrices. Maybe I'm going to turn this into we're a little bit out of time, but I might turn this into a blog post, and I might try out like offline the way of turning this into a 3-dimensional matrix by the center letter, because really what we're doing is we're multiplying. We're adding another dimension, which is this this binary dimension of does it contain this letter. I'm just thinking for a moment. Oh. Yeah. Yeah, I mean we could, but no, that's gonna take a little bit of work. And I'm not gonna do it. I'm not gonna do it now. So far I'm feeling good about center letter R, and these are the other ones. What if I tried making, because R is so far the best, if I tried get score R and then get score of, so it takes R, E, I, A, N, T, G, takes the R's first one. It confirms that R, E, I, and A, T, G, this is at least the maximum we've seen so far, 4,300. I don't have proof that it's the maximum, and I don't know, I thought that E would be the best center letter, so I, just for kicks, I'm gonna confirm that G is the best. I'm kind of just like iterating between approaches here, that G, I'm confirming G isn't better as a center letter. No, it's not. It's considerably worse. And I did not do T yet. T is a common letter, I wonder. But T is a common letter because it's in V. Yeah. All right. 1 second. Almost. Yeah. So, So this turned out to be way more interesting. So I originally misinterpreted this puzzle as being find the highest combination with these honeycombs. It turned out to be a much more interesting question, which is maximize the score for a honeycomb, and that took us into some really interesting matrix directions. Notice something about this. Notice that first I took a tidy approach where I used where I set up our words. I looked for the number of points that each of them would score. I filtered for them, I took did some tidy approach here where I said what is a total score, and I used get words, which for R and our other combination we could discover, and this was like, I'm gonna keep this in because this is get words. So notice that was like nice, but really, and like so words like reaggregating with this combination to get 28 points and 537 total words. Okay, and yes, so this was the best score that I found so far. But then I started getting into this word matrix approach, where we actually said, let's turn this into a binary matrix. With one row for each word and one column for each letter. We dropped out the S's, and then once we applied that, we got this kind of name vector, and we started being able to we started being much more able to to work with a faster get score approach. I even did some applied to that, but the fastest approach came when we possible honeycombs. The fast approach came when we went another layer up in our vectorization, and we actually said, let's create a matrix of all combinations of words and letters, then letters and combinations, and then multiply those together to get a word in combination. This probably can be a little bit more fine-tuned and maybe made a little faster, and I still have some work to do, but I think I'm going to be turning this into a blog post. So it was really exciting to actually show, I'm glad I got to show my thought process as I was approaching a puzzle problem and show how I might take a kind of intuitive and very tidy approach and then turn it into a more performant matrix approach. I'm going to be excited to turn this into a blog. All right. That's it for me. Thanks very much for following me along in this really interesting and deep journey into puzzle solving in R. And I hope you enjoyed